Okay, today's lesson is going to continue with our rational and irrational numbers. This is part 2, lesson 1.13. So you had an introduction to rational numbers. If you have not already had a chance to do so, please visit the following bit.ly address, and that will take you to the rational number video that will kind of summarize and help you identify and classify numbers by their sets in the real number system under rational numbers as rational, integers, and whole numbers. It also, part of the real number system is our irrational numbers, and we will be talking a little bit about those as this week progresses. So here is that diagram from that video and from those notes. As the real numbers, we have our rational numbers and our irrational numbers. The rational numbers include integers and whole numbers. You know that the whole numbers are definitely numbers like the numbers 0, the numbers 1, 2, 5, all of the positive integers are whole numbers. The integers include the whole numbers, that's why that circle is included in the blue outer circle of integers, but it's all the whole numbers and their opposites. So you have -2, you have -100, and it just goes on and on and on of all the negative numbers, plus then also their opposites, the whole numbers and positive numbers as well. And then back to rationals, that's basically, if you think about the number line, the rational numbers fit between those integers. Okay, so a whole number is a rational number. An integer is a rational number, but you also have things like 2.5 and 0.7 repeating, and it's all those terminating and repeating decimal numbers. That brings us to irrational. What do we do if we have a number such as pi, where it neither terminates nor repeats, or we have the square root of 3, that is not a perfect square? So we have to have a place for those as well, and those cannot be written as a ratio of two integers. They cannot be put into a fraction, or they will not be a repeating or terminating decimal, and that's how we would classify and understand the meaning of those numbers. So today we're going to be learning how to write our fractions as decimals. The directions say round to the nearest thousandths if necessary, and I don't believe we'll have to worry about that. The first thing is to understanding the parts. You have the numerator, you have the denominator. That fraction bar indicates division. So what's happening here is 7 is being divided by 9. We know that we cannot take 7 into 9, so we would have to add a decimal and a 0. Bring that up to be part of your solution. You can put a leading 0 if you'd like. Then take 9 into 70, which will go 7 times. 7 times 9 is 63. And when you subtract, you'll get 7. Again, you can't take it into 7. Bring down a 0. And if you see what's happening here, you have this repeating pattern. This is an example of a repeating decimal. So it'll just go on and on and on and on. But we could stop there, and when we show our answer, it could be 0.7. Use the Repetin bar, and we only need to put it over one number, because 77 repeating is the same as 7/10 repeating. So 7 over 9 is equal to 7/10 repeating, which is a rational number. In this example, we have a mixed number, 2 and 11/25. We want to round, again, to the nearest thousandths if necessary, but in this case probably not, so write the following as a decimal. We start off with that leading number, that 2. We know that when you have a mixed number, it's 2 and a little bit more, so 2 point something. And we'll find that by taking 11 and dividing by 25. Again, it will not go in, so we add a decimal point. And take 25 into 110, and it goes in there 4 times, which is 100. Bring down 10 and another 0. 25 goes into 100 4 times. And this is what we talk about with a terminating decimal having a remainder of 0. So our answer in this case is 2.44 or 2 44 hundredths. If we were to write this decimal as a fraction in lowest terms, the first thing you'll want to do is read the decimal in its place value terms. So 15 hundredths sounds in actuality as a fraction, 15 hundredths. Now, in lowest terms means we divide out any common factors. So we know that this has a common factor of 5. And in lowest terms would be 3/20ths. And 12 98 hundredths, same thing. When you have a mixed number, that 12 becomes the larger number. Read the decimal, 98 hundredths, in place value terms. It is even, so we will divide by 2. And then we will write our answer in lowest terms, which is 49/50ths. And then what about our repeating decimals? So we're going to watch this video. It's going to help us find a pattern and be able to write those repeating decimals no matter how many digits are repeating.
Hello mathematicians. After today's lesson, you will be able to convert repeating decimals into fractions, thus proving they are rational numbers. You've learned previously that a rational number is any number that can be expressed in the form a over b, where a and b are both integers and b is not 0. We've learned this includes integers, all fractions and mixed numbers, and any decimal that terminates or repeats. Now, that is the tricky part for us here. Because previously, all you have been told is that repeating decimals are rational. But are you sure? Can you prove it? Can you write it in the form a over b, where a and b are both integers and b is not equal to 0? This baby's not so sure, he's a little skeptical. You should be as well. You may have seen at least one example of this before. For instance, the number 1/3 is clearly rational because the numerator and the denominator are both integers. And when you convert it into a decimal by dividing the numerator by the denominator, you continue to get 3's as you divide. So 1/3 does equal 0.3 repeating, and therefore we've shown that at least one repeating decimal is rational. Is that good enough for you? Oh, this baby's still not convinced, and neither should you be. We've only shown one specific example. What about 0.8 repeating, or 0.12 repeating, or 0.328 repeating? Can I write each of these as fractions and therefore make them rational? I'm not sure. You've been told these are rational, but today we'll prove it by learning how to write each of these repeating decimals as fractions. Let's start with 0.8 repeating. Now, if this had been just 0.8, you could read it correctly as 8/10ths, which is pretty easy to write as a fraction because as you say it, 8/10ths, you automatically make a fraction out of it, and therefore you can tell, oh yeah, that's rational. But this is not 8/10ths. This is 0.8 repeating. So we don't just stop at 8 and say 8/10ths, or even 88 and say 88 hundredths, or even 888 and say 888 thousandths. These 8's continue on forever and ever and ever. We're never going to be able to stop, and therefore, unlike terminating decimals, repeating decimals will not have a multiple of 10 in their denominator. There is a fun algebraic process for changing repeating decimals into fractions. Unfortunately, I don't have time to show it to you here, so I'm going to have to just give you a pattern for converting repeating decimals into fractions. To convert a repeating decimal into a fraction, take the numbers that repeat, called the repetend, and place them over as many 9's as there are in the repetend. For instance, if only one number a is repeating, you would put that number a over 1 9. But if there were two numbers repeating, such as bc, you would put bc over 2 9's. If three numbers were repeating, xyz, you would put xyz over 999. So let's try that with 0.8 repeating. There is only one number in the repetend, so we take the 8 and put it over just 1 9. So 0.8 repeating should equal 8/9. we always need to check to see if that's actually true. So let's go ahead and set up division to make sure that 8/9 will equal 0.8 repeating. We divide 9 into 8. As you can see, this pattern keeps going. So yes, 0.8 repeating does equal 8/9. We have now shown that 0.8 repeating is a rational number, 8/9. So let's continue on to 0.12 repeating. According to our definition, this should be rational because it's a repeating decimal, but let's prove it to ourselves by writing it as a fraction. So according to the step I just gave you, we should be able to write this as 1, 2, because there are only 1 and 2 in the repetend, and we put it over 2 nines since there were 2 numbers repeating. Now this time the fraction actually reduces, and it reduces to 4/33, and it's always good to just prove this to yourself to prove that this actually is an equivalent statement. So I want to make sure that is 4/33 really equal to 0.12 repeating? As you can tell from these first few steps of division, it looks like that pattern is going to keep going over and over again. 1, 2, 1, 2, 1, 2. So again, we've shown that 0.12 repeating is equal to 4/33, and therefore it is rational. One last one here. 0.328 repeating. This time, how many numbers do we have in the repetend? We have 1, 2, 3, so 328, and we put 3 nines in the bottom, 999. So 0.328 repeating should equal 328 999ths. Always good to check, but this will take a little bit, so I'm just going to go ahead and show you all my steps right here. So there you have it. You can now convert repeating decimals into fractions, thus proving they are rational numbers.